So welcome you for afternoon session, and Professor Indrava Roy of our institute, he will be speaking on Laplace transform. So please, I reiterate again, it's an interactive session, and we will be very happy if you participate. It should not be a monologue. All right? Thank you.
Thanks. So, like he just said, please feel free to ask questions. And anytime you feel that the class is going too fast or too slow, please let me know so that I can adjust the speed accordingly. So let me first write down my name so that my name is Indrava Roy, and my email ID is indrava@imsc.res.in. So if you have any questions later on also, you can just send me a mail and I'll try to reply.
One more thing I wanted to add.
Yeah.
So this talk is being recorded, so there is no need for you to take notes. We will put on our website. So pay attention.
And one more announcement, the tutorial classes that I'll be taking will be one on Tuesday, so tomorrow, and Friday. So the timing is 15:15 to 16:45, and it's the same. Okay? All right, so let me just give an outline of what we will talk about tomorrow, what we'll talk about right now. So outline, yes, please. So first we will talk about the background and motivation for Laplace transforms. Okay. So why do we need to study it? Why is it important? And why you should teach your students Laplace transforms. Secondly, I'll give some basic examples. So just some easy examples to start the process of learning, getting to know Laplace transforms. And the third part will be about existence criteria. Criterion, we'll just have one existence criterion, so we will see when a Laplace transform exists and what are the conditions, sufficient conditions for existence. Some more examples. So once we know what are the existence criteria, we can say that the Laplace transform of a certain function will exist because it satisfies the existence criterion, and then we can try to compute what will it be, right? So elementary functions. And then if we have time today, then I can discuss some basic properties. Of Laplace transforms. Okay. So this will be sort of the general outline. You can stop me anytime during the lecture to ask questions. And okay, so let's start. So what is a Laplace transform, first of all? Before we go to a Laplace transform, we should ask, what is a transform? Can you read what I'm writing on the board? Good. What is it? Transform. So transform is a process or an operation. Is an operation, is a mathematical operation. Operation that takes as input a function and gives as output another function. So since you are from engineering colleges, you might be using the black box diagram a lot. So you have some input and you have a black box which is some transform. Let's say call it t. Okay. So let's say input is some function f with parameter t. And the transform gives as output another function, let me call it f with capital F, with a different parameter s, okay? And this is all it does. It takes as input a function with parameter t and it gives you some output, okay? And you have various types of transforms. Can I erase this? The one we will be interested in are called integral transforms. So the Laplace transform is a special case, a special example of an integral transform. And what is an integral transform? So you know that the transform will take as input one function and give you another function, right? So let's say f of t is your input function and you apply this transform t and it will be called an integral transform if, so this is a function of s, okay? So let me write f of s. If it is an integral like this, kst ft dt t plus t1 to t2. Okay, so the name is self-explanatory. It's called an integral transform because it's given by an integral, right? So kst is a function of two variables. Kst is a two variable function. And by this integral, you get another function which depends on s. Because you're integrating out the t variable from t1 to t2, you're left with only the s variable, right? So that's why you have only the s on the left hand side. And there are different types. So first let me say, so this formula might look a bit strange at first. But if you think about matrix multiplication, everybody knows matrix multiplication. So let's say A is some big matrix, A11, A1n, A1n, ANN. So this is an n cross n matrix, right? You can apply it to a column vector, x1, x2, x3, and so on, xn. And the result will be another column vector, y1, y2, yn, And what is the formula for yk? Using this. So the formula for yk is the sum I equals 1 to n. Sorry? Yeah, so it's a ik xk. Sorry, aki xi. Right? So now here we have discrete variables. So here k and I are discrete variables. They are taking only numbers, integer natural numbers 1, 2, 3 to n, right? So I and k are discrete variables. So if I write without the subscript like a function yk I equals 1 to n a k I x I. So you can think of yk as a function of a discrete variable k. You can think of a as a function of two discrete variables k and I, and x is also a function of one discrete variable I, right? So if you change from discrete to continuous, okay, so change your k to s, your I to t, and your summation to integral. What do you get? You will get ys is integral a s t x t dt, right? And this is exactly this formula here. Okay, so your capital K here is just your continuous analog of a matrix. Okay. So in this sense, Laplace transform or in an integral transform is the continuous analog of matrix multiplication. So let me give some examples of integral transforms. So you just have to specify this function k. By the way, this is called the integral kernel. So you have to specify the integral kernel of the integral transform, and you have a well-defined integral transform. So examples include Fourier, one of the most famous transforms, and for this k s t is what? 2 pi I s t. And your limits of integration t1 and t2 are given by t1 is minus infinity and t2 is plus infinity, right? Another integral transform is called the Mellin transform. So here k st is given by t to the s minus 1, right? T1 is 0 and t2 is plus infinity. Okay? So let me just go straight to Laplace transform. So here k of st is exponential minus st. Okay? t1 is 0 and t2 is plus infinity. So the notation that we are going to use we write fs for the Laplace transform. Sometimes you can also write L with the calligraphic L of ft. So this is your input function. You apply your Laplace transform and you get another function, right? And this is integral 0 to infinity ft e to the minus st dt. Yes. How can you? Right, that's a good question. For example, the Fourier transform is given by change of basis in a Hilbert space, if you want. And the Laplace transform is sort of a continuous analog of a power series. For example, if you have, so let me write f or gx to be sum a n x to the n equals 0 to infinity. So this is a discrete, a n's are discrete, x can take any value, right? Now if you put a n again like the process I did, if you put a as a function of n and x as a function of n, okay, sorry, x is a variable. You just take a to be a function of discrete function of a discrete variable. Now this power series, suppose a n is all 1 for all n, right? What will you get here? It's a geometric series. What will be the answer? 1 over 1 minus x. Something else? Right. So mod x must be less than 1. So you see that you can hope to have a convergence series as long as mod x is less than 1. Right? So let me restrict even to 0 less than x less than 1. We want something positive. Okay. Then what you can do is follows. So write out the continuous analog of a power series. So you will have g x is a t x to the t, okay, dt, okay, 0 less than x less than 1. This is the continuous analog of that power series. Now you make a change of variables. Write x to be e to the minus s. Because x is between 0 and 1, you can take any positive s and x will be between 0 and 1. And what will you get here? 0 to infinity at e to the minus st dt. What is this? This is the Laplace transform. So you can think of the Laplace transform as a continuous analog of a power series. Okay. Otherwise, there are many other integral kernels that you can choose, and they are sort of dictated by the problems that you're working on. Okay, it really depends on what kind of problems you're working on, and when you're trying to solve these problems, these integral kernels will naturally come up. Okay. So I've defined what is a Laplace transform. So let me just say one thing. This is this integral 0 to infinity ft exponential minus st dt is an improper, so this is a remark, is an improper Riemann integral. So when you're talking about integrals, there are many ways to define an integral, and the Riemann integration is the most basic one. Okay. But usually when you're defining a Riemann integral, you have finite limits of integration, right? Now to define 0 to infinity, this is by definition it is a limit of r tends to infinity, 0 to r ft exponential minus st dt. Okay, you first integrate over some finite interval, and then you take the limit as r goes to infinity. This is a definition. Okay, this is by definition. Okay. So let me just solve some very easy examples of Laplace transforms. So easy examples of Laplace transforms. So now that we have a formula, we would like to compute the Laplace transform for specific functions. Right? So the first one is just take ft to be 0 for all t positive. It's 0 everywhere. Right? Then what will be the Laplace transform? 0 to infinity ft dt, right? And ft is 0 on this interval, 0 times e to the minus st dt. So this is just 0, right? This is a very easy example. Another easy example that one can think of is to have, rather than 0, have any constant, any real constant. So ft is c, where c is a real constant. It could also be complex, but let's just take real for the moment. Then what is fs? ft so this is just c e to the minus st dt 0 to infinity. And what is this integral? One by s. So let's be more careful. Okay, let's write it out as an improper Riemann integral. Okay, c limit r tends to infinity 0 to r minus s t dt. Now this integral is easy to compute. This is e to the minus r st over minus s 0 to r, right? So what do you get? C. First you put r, exponential minus sr, then you put 0, so you get 1 over minus s, right? Now the limit as r goes to infinity, you say that is 0, but you have to put the constraint that s must be positive, right? If s is not positive, then it will blow up and the limit will not exist. Okay, so this is c over s if s is positive. So the limit exists only in this region. Okay, so since we are talking about existence, let me maybe just do another example. So let's take t f t is t to the n is a positive integer. Okay, so let's try to compute fs. Because this depends on n, let me put a subscript n here. So the Laplace transform will also depend on n. N is fixed. Okay, so this is t to the n exponential minus st dt 0 to infinity. What can we do for this? Any ideas? Huh? Change your? You can change a variable to what? Sorry, just you want a gamma function? Oh wow! So you guys are always way ahead of me already. Okay, yes, you can use a gamma function. And then you want to use that the gamma of n plus 1 is n factorial, right? I don't want to do that. I want to do it by first principles. So then we use integration by parts. Okay? This is a standard method for computing Laplace transforms. Okay? Use integration by parts. What do you get? You get 0 to. So first, I take u. So for integration by parts, you need to choose your functions appropriately. You take u, u equals t to the n, and v equals e to the minus st, right? Then first you have to integrate v and keep u constant. So you have t to the n exponential minus st 0, sorry? Right. You have to divide by minus s. 0 to infinity minus 0 to infinity n t n minus 1. So you differentiate u, integrate v, minus st minus s dt. So this minus and this minus becomes plus. Now if you want to evaluate this limit, at 0 this is just 0 because this exponential is s0 is just 1, and you can just put t equals 0, so you get 0. At infinity, what do you get? 0, because this is a polynomial and no polynomial grows faster than an exponential, right? So this always wins when it goes to infinity with respect to a polynomial. So this is just 0, and then the second term is n over s, and note that fns is t to the n e to the minus st, and here you get t to the minus n minus 1 e to the minus st. So this is f of n minus 1 of s. And here again we have made this implicit assumption that s is positive, right? So now it becomes like a gamma function. So you get f n s is n over s f n minus 1 s, s is positive. So you can just keep substituting for lesser and lesser values of n, and you will get n over s, then you have n minus 1 over s, and this will continue until you hit what? 1 by s, right? So then you have f0 of s, right? So this is n factorial over, here you have n terms, s to the n, and what is f0? Right, f0 is just this guy where c equals 1, right? So here get c by s, so you just get 1 by s. So here you add around here, okay? This is for s positive. Good. So we have seen how to compute easy examples. Now let me say something about existence. So you have seen that fs may not exist for all values of s, right? And fs may not exist for any value of s also. So we need some criteria for which, given a function that satisfies that criterion, you can say that the Laplace transform will exist for some value of s. Okay? So this is existence criterion for Laplace transform. So here we will only talk about sufficient conditions for a resistance. Okay. So this existence, this terminology is key. What does it mean for a Laplace transform to exist? It means that this formula Fs limit r to infinity 0 to r ft exponential minus st dt, this limit exists. So we say that the Laplace transform exists. We say that Fs, or the Laplace transform, exists if and only if the above limit exists, meaning that it is finite. Okay, it could also be infinite, that then also it exists, but by exists I mean it is finite. So you must get a finite value as r tends to infinity. And the values of S, let me write it here. So this is a definition, you can take it as a definition or a terminology. The values of S for which limit infinity 0 to r exists taken together. Let me take the set of values. The set of values of S for which this exists is called the region of convergence. Okay, of F. So for example, the region of convergence here is just the positive thing. Okay, actually it's also, you can take towards the complex, extend to the complex plane, but for us let's keep things simple and we'll just work on the real line for the moment. Okay, so the region of convergence in this is just the positive real line, 0 to infinity. Okay, this is the region of convergence. Okay, so now I'll make two definitions which will give you the existence criteria for Laplace transforms to exist. So the first one, definition, this is about piecewise continuous functions. Sometimes they are also called sectionally continuous. Okay. So definition, a function ft defined on a finite interval a less than equal to t less than equal to b. So here a and b are real numbers, is said to be piecewise continuous if this interval AB can be subdivided into subintervals which I can label IK, TK minus 1 to TK, okay, such that, so bear with me, this is a bit longish definition, such that FT is continuous on IK and the left hand and right hand limits at each endpoint, exists and is finite. So what does this mean? So you know intuitively what a continuous function looks like. So it's a continuous curve, right? So let's say our interval is here is A, here is B, and you want to subdivide this interval into smaller intervals, and our function is no longer continuous on the whole thing. So you have T1, T2, Tk, okay. Like this, and rather than the function being like this, it is sort of something like this. It goes here to T1, but the left hand limit and the right hand limit are not the same. Here they are the same. If you approach it from the left, if you approach it from the right, you end up with the same value. But here it might be different. So it might be something like this. Okay. The left hand limit and the right hand limit still exist, but the function is not continuous at this point. Okay. It could also take at this specific point T1, it could take any value. It need not be this value or this value. It could take any value, but finite. Okay. And similarly for other intervals like this, so it's broken up into continuous pieces. That's why it's called piecewise continuous. Okay. So the function is something like this. So it's continuous on each subinterval. It is continuous, and the left hand and the right hand limit at each endpoint is finite. So, for example, if you have a function for which this goes to infinity and this goes to infinity, this is not allowed. Okay, this is not allowed. You have to have finite limits from both sides. Okay. So we need another definition. A function ft is said to be of exponential type if it is if for any t not positive, okay, it is piecewise continuous on 0 less than t less than t naught, okay, and for all t greater than or equal to t naught, it satisfies or let me write it down. There exists for all t, there are constants alpha and m such that this inequality holds. So what is the inequality? ft exponential minus alpha t is less than or equal to m. So for all t large enough, so this is the behavior at infinity for this function f. When you go towards infinity, it does not grow faster than the exponential. Okay? If it grew faster than this exponential function, then it would not be bounded. There will not be a bound for this function. Okay? So for this, we need that the function decays towards infinity. Okay? Okay. So sorry, it may not decay towards infinity all the time. You only need that it does not go faster than the exponential function. So the theorem, this is the existence theorem. Is that if ft is of exponential type, by the way, this constant alpha, we say that ft is of exponential order alpha. So if ft is of exponential type, then with exponential order alpha, then the Laplace transform Fs exists for all s greater than alpha. So you found a region of convergence for the Laplace transform. Okay. This might seem a bit theoretical, but why do we need existence theorem? Because if I give you a random function ft with a big formula, first you would like to know before starting to compute that its Laplace transform should exist, right? It turns out that you spend days on end trying to compute what it is, and in the end you found out that it doesn't satisfy the existence theorem. Okay. So this is why one needs existence theorems to check whether its Laplace transform will exist or not. Okay. So in our examples, so what are the examples of functions of exponential order? Examples. So in the examples that we computed, first one is constant. Is this of exponential order? Yes? Actually of order 0, yes. Yes. So in fact you can take any positive alpha in the program, right? Because you can always find, so let me write down C. So what you want? You want C is less than or equal to m alpha t for some. So C is a constant. We want T naught such that C or mod C is less than or equal to m into the alpha t for all t greater than or equal to T naught. And this is easy, right? Because the exponential function will grow faster than the constant function. Okay, so you can just take, what can you take? You can take m to be 1, take m equals 1. And if you take log on both sides, so suppose that C is positive, or you can, so log mod C is less than or equal to alpha t, right? This is an equivalent condition. So if t is greater than or equal to log mod C over alpha, then you're done, right? You have found a T naught, so this is your T naught. So ft is of exponential order for any positive alpha. Okay. Second example, ft is t to the n. Is this of exponential order? Yes, because as we know, polynomials don't grow faster than exponentials. So, as an exercise, find m, alpha, and t naught for this function. Okay. This is an exercise. As a non-example, meaning that a function not of exponential type, you can take ft to be exponential of exponential t. Okay. Again, exercise. Prove that ft is not of exponential type. I'll leave it as an exercise, so we can discuss it in tutorial if you want. Okay, so we want to know what kind of functions are of exponential type, what kind of functions aren't of exponential type. So we have seen some examples. So now we know that if a function satisfies this condition, then the Laplace transform will exist. I thought of doing the proof of this, but let me move on and compute some more examples. Maybe I can prove it also in the tutorial classes or in the next classes. For the moment, I leave it without proof, okay? More examples. This. More examples. First is ft sine t. So is this of exponential order? Yes, because it's bounded. Bounded functions are always of exponential order. Okay. So first we know that ft is of exponential type with some order which we don't care for now. So we can just start to compute the Laplace transform of ft. Sine t exponential minus st dt. So how do we compute this? Any ideas? Integration by parts, yes. So again, one of the basic methods to compute Laplace transform is by integration by parts. Okay. So let's do integration by parts. What will we take as u? Take sine t. Okay. For v, we take e to the minus st. Okay. So what do you get? We'll get sine t exponential minus st over minus s, 0 to infinity, minus differential of sine t cos t exponential minus st over minus s, so this becomes plus 1 over s, 0 to infinity. So we can evaluate these limits. At 0 it's 0 because sine 0 is 0, and infinity sine t is bounded, so it's of exponential order, and this goes to 0. So this is 0, and you have the Laplace transform of cos t. Yes. So we can do the same game again. You can do the integration by parts. So now you take u equals cos t, v equals e to the minus st. So first you get cos t exponential minus st over minus s, 0 to infinity, minus 1 over s, 0 to infinity. Differentiate this, get minus sine t, and you have integrated this. So this integration factor is coming out. So you have 3 minuses, so you can retain the minus here. what is this limit? So you have 1 over s. At infinity it is 0, and at 0 is 1, right? Because cos 0 and both e to the minus st both are 1. So you have minus 1 over s, and you have minus, sorry? Oh, yes. Thank you. Yes. 1 over s, and you have minus 1 over s, and this is again your f of s, right? F of s. So you can take out 1 over s, so get 1 over s square, 1 minus f of s. So what is the equation that you get? Okay, so fs, this is on the left hand side, way up there, and on the right hand side you get 1 over s square, 1 minus fs. So we can solve for fs. So when you solve, you get 1 over s square plus 1. And again, we have made this, when we have evaluated these limits, we have implicitly assumed that s is greater than 0, right? So this is for s greater than 0. Okay? So what about cos t then? How do you say that? You can just read it off from here, right? This one is 0. Okay? So let me write gs, maybe f prime s to be the Laplace transform of this one. Then f prime s is equal to 1 over s f prime s is equal to I made a mistake. 1 over s f prime s is fs, which is equal to 1 over s square plus 1. So what is f prime s? This is s over s square plus 1. Right? Is this clear how I get this? I just use this formula here. On the left hand side you have fs, and on the right hand side this part is 0, this is 1 by s, and this is f prime s, right? This whole thing is f prime s. So you get 1 over s f prime s, this is this one, and on the right hand side you have fs. Okay? That's how I got this equation. And fs you have already computed to be 1 over s square plus 1. So f prime s is s over s square plus 1. So I think I'm out of time today.